Okay, this is a bit of a sadistic problem because the easiest way to do the problem is to use the shell method. Now, this y-axis is our axis of revolution. I've got the green graph here as g of x, 2x squared minus 8x plus 9. The red line is f of x. And if we were going to use the shell method, we would consider a typical shell parallel to the axis of revolution, and the distance or the radius of a typical shell would simply be x, the distance from the axis of revolution to the center of the shell, and the height of the shell would be f of x minus g of x. So that's what this is right here. Now you could get an answer in terms of pi. Desmos gave me the decimal approximation here of 141.37. Okay, but you're asked to do this using two rules, using the washer method. So that means that we want our typical shells perpendicular to the axis of revolution, which is why we have to have two different integrals. One from 3 to 9 along the y-axis, because this will be a typical shell region. And then down in here, we'll have this. And so for the washer method, we're using the formula pi times the definite integral from, in this case, 3 to 9 of outer radius squared minus inner radius squared. So outer radius and inner radius are x values depending on the y value. So we have to solve each of these functions or equations for x in terms of y. For the linear function, that's not too bad. X equals y minus 1 all over 2. To solve this quadratic function for x in terms of y is not so easy. I'll give you some hints here. We could do this. Eight x plus 9 minus y, treating y as a constant. And now we've got a quadratic equation, and we could use the quadratic formula to get x in terms of y. So it would be the opposite of b, plus or minus. The plus will be the outer radius. The minus will be the inner radius of b squared minus 4 times a. 4 times 2 is 8 times c, but c is 9 minus y. And all of that is over 2a, 4. Now you can clean that up quite a bit by distributing this minus 8, factoring out an 8, and taking the square root of the 8, blah, blah, blah. Now the point is that this region right here, if we rotate it, I'll call it a sub 1. Maybe I should have called it r sub 1. If we rotate that region about the y-axis, a formula would be pi times the integral from 3 to 9 of the outer radius squared. Well, that would be 8 plus, and I'm just going to write the square root symbol here, all over 4, the quantity squared, minus the inner radius would be y minus 1 all quantity squared. And if I put this in brackets and say dy, there would be the formula for the volume you get by rotating region a sub 1. If I call this region or area a sub 2, the volume, I'll call this v sub 1. V sub 2 would be pi times the definite integral from 3 to 9 of outer radius squared would be this 8 plus the square root all over 4, the quantity squared, minus the inner radius squared, 8 minus that square root all over 4, the quantity squared, dy. And then we would add those two volumes together, and we get the area or the volume of the solid of revolution. This looks pretty bad. If you simplify this and then do the subtraction or the squaring and the subtraction, it gets a little simpler. You have to use U substitution to actually evaluate the definite integral, but in fact it does work. And I will include a link to the Desmos graph where I got this picture, and it shows you that indeed the two volumes are identical.